Hi, my name is Talon Ward, and this is my recorded backup demo for an Introduction to Logarithms teaching demo for Lansing Community College. Today we'll be talking about logarithms, for the first time for Precalculus class. Okay, so today we're talking about logarithms, and we've gone over exponential functions, right? So let me remind you what an exponential function first is, because logarithms and exponentials are intimately related. Okay. So an exponential function is a function of the form y equals b to the x. Okay? And b is some base, it's positive. So b is greater than 0. And we're usually not very interested in b equals 1. So we'll just go ahead and say b is not 1. Right? So that's our exponential function. We take in an exponent x and give out the result of exponentiation by x for a fixed base b. Okay, so now I'm going to tell you what a logarithm is. So logarithmic function. Logarithm is just the inverse of an exponential. Now we've talked about inverses, but I'll just remind you what that means. So an inverse, we switch the x and y. Right? So an inverse takes an operation and undoes it. In this case, we took an exponent and then we exponentiated b by that exponent. So in the logarithmic section, the logarithmic function, we're going to switch x and y, and we're going to have the function x equals b to the y. You know, not revolutionary, right? But our perspective has changed. Our input isn't the exponent this time. That's our output. We're getting back the exponent. So the logarithm is the exponent that you need to use to get to your input. So we're going to write this as, this is the notation we'll use, log base b of x equals y. So these are the same. This equation and this equation both mean the exact same thing. So if you ever see log base b of x, just think that's the exponent. To the base b to that exponent gives me x. These are the same thing. Same thing. All right. So let's look at an example. What do I mean by this? So what is a log base 2 of 8? Well, it's the exponent that I need to take 2 to get 8. So 2 to the 1 is 2, 2 squared is 4, 2 cubed is 8, right? Okay, so that's log base 2 of 2 cubed. And looking up here, we see, oh, it's the exponent of my 2. So it's 3. Okay. How about another example? Let's do log base 2 of 1/9. Log base 3 is what I meant to say. So what is log base 3 of 1/9? Well, 1/9 is 3 to some power, right? 3 to the negative 1 is 1/3. 3 to the negative 2 is 1/9, right? So this is log base 3 of 3 to the negative 2. And we're just taking the exponent off from our base 3. Our answer is negative 2. Makes sense, right? Okay. So obviously we're not always just going to be taking logarithms of numbers. We're going to be solving logarithmic equations or solving equations with exponents using logarithms, right? So let's look at some really basic examples of that before we move on. So we could just do the same example we just did, but a little differently. So I want to solve the equation 2 to the x equals 8. Now you can't use normal algebraic techniques on this because you have an exponent. How do you get into that exponent? Well, whenever you have an exponent that you're trying to get into, that's what you use logs for. So a logarithm is a tool in order to access and manipulate exponents in exponential equations. So this is an exponential equation, and we want to solve it by taking logs. So since we have a base 2 here, it makes a whole lot of sense to use our b equals 2. Let's see what happens if we take the log base 2 of both sides. Well, the log base 2 of 2 to the x is just the exponent that you take 2 to get 2 to the x, but that's x. So like we said, inverses, log base 2 of 2 to the x, they cancel each other out, and you just get back your original x. So x equals log base 2 of 8 equals 3, which, because we just did that, right? Okay, so this isn't, profound, or maybe it doesn't seem profound, but that's because we knew this, right? But what if we didn't know what we were doing? We didn't know that 8 was 2 cubed. What if it's not even an 8? What if it's 2 to the x equals 9? Now what are we going to do? Well, we take the log base 2 of both sides. We get an x on this side. And this side, what is that? Log base 2 of 9, right? What else am I going to do with that? This is a number. It's the exponent that I need to take 2 to get to 9. I know it's bigger than 3 because 2 cubed is 8. And I know that it's smaller than 4 because 2 to the 4th is 16, right? And 9 is between 8 and 16. But it's not clear what exactly is this number. And it's irrational number. It's a pretty crazy number. So when we write it out, we're just going to leave it like this. So logs are convenient in that they help us encapsulate this idea of an exponent. Now you can plug this into your calculator and get a nice decimal approximation of log base 2 of 9. It should be closer to 3 than it is to 4, right? Because 9 is pretty close to 8. But it is on an exponential scale. So we're going to have more complicated problems than this. Not a lot more complicated, but we're going to look at some more complicated ones and apply it to exponential growth later, but not today because we only have 15 minutes. So let's take a look at what this log is a function, so we can graph it, and let's take a look at what that graph looks like. All right, so to graph logarithmic functions, we're going to cheat a little bit. All right, because we already talked about exponential functions. We already graphed exponential functions. We know about asymptote for exponential functions. And since this is the inverse, and we know the relationship between functions and their inverses graphically, we can use that to figure out what a log looks like without a whole lot of effort, right? So I'm putting this dashed line y equals x in there, and I'll remind you why. It's because the inverse of a function graphically is reflection around the line y equals x, or about the line y equals x. So let's look at exponential graphs first. Our exponential graph, well, our exponential function was y equals b to the x. And we had two different cases that we were concerned about. All right, well, there was the case when b was greater than 1, and the case when b is less than 1. So when our base is bigger than 1, that means as our exponent grows, our output grows because we're multiplying over and over again by numbers bigger than 1. So this is going to be an increasing function, or an exponential growth function. And our case where b is less than 1, or since we're considering b positive, we can say 0 is less than b is less than 1, is going to be our decreasing exponential decay function. Okay, so let's consider one case at a time. So the first case, b is greater than 1. So case b is greater than 1. So we know what this looks like, the exponential function. It's got this 0.01 because anything to the 0 is 1, right? So b to the 0 is 1, no matter what b is. So we got this point on here. We have an asymptote, horizontal asymptote at negative infinity, and it's increasing and grows exponentially. So it does this, and that is our b to the x. Now what's another point that is also on this graph? Well, an easy point to pick, if you're picking easy numbers, I like easy numbers, right? B to the 1, that's a pretty easy number. So B to the 1 is B, okay? So on our exponential graph, this was, we put in a 0 and we got a 1, so the point 0, 1, 0, 1 was on our graph. And this, we put in a 1 and we got a B, so the point 1, B was on our graph. And say 1 is here. B is bigger than 1, so 1B is here, is going to be bigger than 1, and it's going to be above. So B is above 1 here. Here's our 1. Wow, that's a terrible 1. All right? Okay, so let's look at the logarithmic one. The logarithmic version is going to be this reflected, right? We're going to reflect it around this y equals x, and we're going to switch these points. So this point, it's the same equation, just from a different perspective. We switch the input and the output. That is, we switch our x's and y's. So what was an x was 0 now becomes a y is 0, and what was a y is 1 is now an x is 1. So our input, this is log. So here we have b to the y equals x. And over here we had b to the x equals y. So our point 1, 0 is going to be on our log graph. That's this point right here. And our point, we're going to swip it, b1, swip it real good, is going to be somewhere, well, again, b is greater than 1, so we're going to be to the right of 1. Somewhere over here there's a b, and there's a 1. That's our point. And then that shape is just going to transfer right over. So we're going to have an asymptote and pretend that looks beautiful. That's what our graph looks like. Great. So a couple properties. Notice we're increasing. So our graph is increasing. This is our case b is greater than 1. Well, it's right here. Okay, we're increasing, and we have a vertical asymptote. It's at x equals 0, and it goes down to negative infinity. All right, so now we have another case. Our other case, draw some axes over here. Our other case was with b is less than 1, or 0 is less than b is less than 1. All right, so this part right here, this really didn't depend on our b is greater than 1, did it? B to the 0 is 1, whether b is greater than 1 or less than 1. And b to the 1 is b, again, whether b is less than 1 or greater than 1. So these points are still going to be on our graph. So we're going to have, in our log, we're going to have the point 1, 0 and the point b, 1. Let's see. Let's say this is 1. So 1, 0 is here. This is going to be my log function. And b1, well, b is less than 1, so it's going to be less than 1, bigger than 0. Somewhere in here, there's a b, and it is 1 at that point. Okay. So now let's think about what did exponential decay look like. Well, exponential decay was kind of reverse, right? We started off big, and we shrank to a horizontal asymptote at infinity, right? So our exponential case looked like this. This is b to the x, exponential. This was log base b of x. Right? Okay. Well, in our inverse function, we're going to be rotating around this, or flipping it around this point, this line, y equals x, and what's going to happen? Well, it's going to up like this. So this horizontal asymptote goes up to become a vertical asymptote up here. And it's going to come down and go like that. Right? It's supposed to cross right there, but I hope you get the idea. And notice here we are decreasing. And we again have a vertical asymptote. But this time it's going to positive infinity. A vertical asymptote at, I can spell, x equals 0. All right, so that is the time we have for today. It's just a brief introduction, so you can do your worksheets.